morning, good afternoon, good evening. Welcome to the second ISCA Keynote. It's a great pleasure and an honor to introduce our speaker, Professor Monica Lam. Dr. Monica Lam has been a professor of computer science at Stanford University since 1988 and is the faculty director of the Stanford Open Virtual Assistant Lab. She leads the Genie Open Virtual Assistant project, which aims to advance and democratize voice assistant technology, keep the voice web open, and protect the privacy of consumers. Professor Lam is a member of the National Academy of Engineering and an ACM Fellow. She has won numerous Best Paper awards, and she has published over 150 papers on many topics: natural language processing, machine learning, ACI, compilers, computer architecture, operating systems, and high-performance computing. Her contributions in compiler optimizations include software pipelining and affine transformations for data locality and parallelism. The Swift compiler infrastructure developed by her research group was widely used by compiler researchers all around the world. Her contributions in computer architecture include the CMU word systolic array and the Stanford DAS distributed memory multiprocessor. She is a co-author of the Text Compilers, Principles, Techniques, and Tools, also known as the Dragon Book, the definite text on compiler technology. She received a PSc from University of British Columbia in 1980 and a PhD from Carnegie Mellon University in 1987. Professor Lam will present today's keynote on Genie, an open privacy-preserving virtual assistant with deep learning. Monica, the stage is yours.
Right, thank you. Thank you so much, Jose, for the introduction. And good morning, good afternoon, good evening. I think that was really cool. And I'm so glad to be back at ISCA. I've done a lot of work on computer architectures and compilers in the 80s and the 90s. Worked on the systolic arrays with H.D. Kung at CMU. And then when I joined Stanford, I worked with John Hennessy on the shared memory multiprocessors. And then on my sabbatical, I worked with Chris Rowan on configurable cores at Tensilica. So, and then what happened is that I kind of realized that performance is in good hands, and I started working on other issues. And what I've been very concerned about in the last 10 years was the privacy for consumers. It is very worrisome that the billions and billions of people's private data are in the hands of a small number of companies. And 6 years ago, I locked on to this issue of virtual assistant. And we started an initiative to create an open source virtual assistant. And what I'm going to do today is to convince you that, number one, it is a very important topic. It is hard, but it's very important. And we think that we know how to make it happen. All right. So let me start by sharing the screen. All right. And let's get started. All right. The first thing here is that voice is absolutely the third generation computer interface in this world. The first one, we have the terminal with the mainframes, and then with the PCs, we have the bitmap displays and the mouse, and now we have voice, we have natural language. This is the interface for, this is the interface for humans. And so this is the ultimate interface, and we have it now because of machine learning. And the best embodiment of this voice technology is the virtual assistants. It changes how we interface with the computers, right? We don't have to just do keyword searches on search engines. We can just make our queries in natural language. And we don't have to navigate menus after menus because we can just use a dialogue and talk to the companies, on the websites and the mobile apps and IoT devices and whatnot. And what is really exciting here is that we don't have to rely on coders for every line of code to be written, because the consumers can now automate their own tasks in natural language. So this is going to make a huge difference on how we interface with the computers. And the amazing part is that this is a one-stop interface. Okay, through this interface, I can get to all the different IoTs, websites, the banks, and everything. But the flip side is that this assistant knows everything about you. So, and what we are seeing today is an emergence of a duopoly in the smart speaker space. In America, 70% of the US market is taken by Alexa, and the Google Assistant is a far distant second. Alexa is not just an interface to Amazon, it is an interface to over 100,000 third-party skills and 60,000 compatible IoT devices. What it means is that it is a voice web. It is a voice web, but it is also a proprietary web. And this is very worrisome to the business and to industry because they become the intermediary between the consumers and the businesses. They can exert a lot of control. It also has a huge impact on the society because we know that monopolies, duopolies, oligopolies, they're not good for innovation. And when you have a couple of companies that own so much of people's personal data, we have to worry about the privacy issues. And on top of that, this is such an important technology. We cannot have it locked up. We also have to worry about who is going to work on the low resource languages and what about all the nonprofit causes that we can take care of with the power of voice. And whoever is going to win this smart speaker war is going to have the power of Google, Amazon, and Facebook combined because it is really the interface to the web. So the question we want to ask is it possible for us to build an open source assistant? But the problem here is there is an enormous barrier to entry because it is very labor intensive to build virtual assistants. Alexa has over 10,000 employees. Okay, so how are we going to solve this problem? Why is it so labor intensive? Let's take a look at the first party skills, the skills that are made by Amazon for Alexa. Well, you have to understand natural language. And what it means is that you're going to do machine learning, and that means that you need a lot of training data. And what we need is to get real users' inputs, and then we have to annotate it in some formal representation, in this case, AMRL. And this representation is reflective of the source language, of the structure of the source sentence. And so you have to do that for every single sentence, whether they refer to the same meaning or not. So in this case, these two sentences actually mean the same thing, but you have to annotate it differently. And of course, you annotate it differently for all the different languages as well, and you send it through the training. You use this to train the neural network. Well, you'll notice that all these sentences are just different variants of the same sentence. But now there are many possible requests. And this is all just restaurants, but of course there are many domains. And then there are also many, many languages. And as a result, what we see here, it is extremely laborious. And with this approach, you really cannot handle the long tail requests because there are just so many things that people can possibly ask. And what they have done is they build an assistant that is not conversational. You basically bark commands at Alexa and try to get an answer out of it. So this is what they do for the first party skills. For the third party skills, people need dialogues. And the technology used here is dialogue trees. And instead of a semantic parser, a neural network, we are using intent classification for every single term that the developer designs. Okay, so you have to decide what the agent says, what are all the possible things that the user says. But if the user goes off the script, which is very often, as a matter of fact, then it's game over. Okay, you cannot get back into this dialogue tree. And so what it means is that it is not just laborious, it is also very brittle. So in summary here is like labor-intensive part is just one of the issues, but it also has very poor coverage, it is brittle, and it is not easily scalable. The bottom line really is that we have to shift the paradigm. We cannot just rely on annotations. The reason here is that natural language is compositional. We have all, we know a bunch of words, but we put them together in many, many possible different ways. There are many sentences that we can utter, and it is not interesting, it's not enough to just understand the most popular ones. You have to understand the long tail set of sentences that people can create. And so because of this, it prompts us to build a new development technology, which combines deep learning with programming languages. So at this point, I want to give you a status, the status of our initiative, and then we'll go into the details of how we make this happen, okay? So the initiative has three components: Open Tech, the Open Voice Web, and the Open Assistant. We have created a toolkit, we call this Genie toolkit, that helps programmers create voice assistants or voice interfaces very easily. And we use this tool and we build a bunch of skills. And we put the skills into this repository called Thinkpedia. Okay, just like Wikipedia, it is open, it is crowdsourced, and it is non-proprietary. It is open to everybody, open to all assistants. And these skills are used in our own assistant, which is also called Genie, the Genie Assistant. And the Genie Assistant is special in the sense that it also protects privacy. At this point, we have alpha releases of everything, and it is accessible through oval.cs.stanford.edu. Oval is Open Virtual Assistant Lab, which is our lab. Obviously, what we have built is not competitive at this point compared to Alexa or Google, but what we have done is to lay out a technical foundation for open collaboration. Because this is all open source and non-proprietary, our goal here is to get everybody to help build the open voice web. And we think that in about 5 years, we can have one that covers like 300 plus languages. Why 300? Well, there are 300 languages in Wikipedia, okay? And this is the power of open source. If we make it available, then people will do it for their languages and for their knowledge. And that's what we are shooting for. So now let me go into each of these components and give you an overview. So the Genie toolkit allows people to give a high-level spec. It's just like a compiler in a sense. You give me a high-level spec. So for example, if you want to build an answering agent, question answering agent over a structured database, you give me the schemas. If you want me to run APIs, you give me the signatures, all right? And on top of that, you add a little bit of manual annotation, which is about 2% of what people are doing today. And we automatically generate you a conversational agent. And this agent is multilingual, it is also multimodal, but more importantly, it is also programmable. So here are a couple of claims to fame. The first one is that we can answer long tail questions with higher accuracy, for example, on restaurants, compared to some of these very well-resourced commercial assistants like Alexa, Google, and Siri. And secondly, our system is programmable. You can say something like, when the weather forecasts rain, turn off the sprinkler. Nobody else can do that. We have also built an agent that can read natural language instructions and provide customer service, right? So that's the toolkit. And we use this toolkit and we build some skills and we put it into Thinkpedia. For question answering, we have shown how we can take a number of very important domains in schema.org and automatically answer questions about the web. So schema.org is a markup language that about 30% of all the web pages in the internet are using. What they do is that they put information on the website into the structured representation so that the search engines can now use this to answer questions in searches. And so we are leveraging this, and by converting by making the information in schema.org available in these question answering agents, we are now making the web available. And hopefully more people will put more and more information on schema.org, and this is how we can provide information on the web as is. We are also now working on answering questions on Wikidata, which is 100 million items, and this is work in progress. For IoT devices, we are building on the Home Assistant. And at this point, we have 700 plus devices that can that have a voice interface with Genie. And we have also got a number of popular skills like Spotify, Yelp for restaurant information and reservations, news from Smart News, Bing Search, RSS feeds, weather, and of course the important jokes and cat gifs. That's what we have so far at this point. And it is open, and we are, we welcome contributions from everybody. And now let's talk about the Genie Assistant. It's an open source privacy preserving virtual assistant. And currently it is distributed with Home Assistant. It is called Almond. It is our code name during this alpha period until it will be converted into Genie. And Home Assistant is a private gateway. You can run it at home, and you connect to all these different IoTs, and all the information doesn't leave the house. And currently it has about 100,000 users. And what is special about Genie is that it has a federated architecture. So I can run an assistant at my home. You can run one at your home, and somebody else may want to use a web service and so forth. But we can communicate using and the assistants use a secure protocol for communication. And so this architecture supports sharing, and our system supports fine-grained access control in natural language. So for example, I can say my dad can access my security camera only if I'm not home, because I don't want him to snoop on me when I'm at home. All right. So this is a architecture really designed for sharing with privacy. So that's an overview, and now let's go deep into the ideas behind these topics. And I'm going to focus on two things, which is the methodology, how we combine deep learning and programming languages, and how we support sharing with privacy. All right, let's start with the toolkit. So instead of a representation that reflects the source language, we have created a language called ThinkTalk that we use to represent the natural language semantics. It is a formal programming language. It executes, okay? And ThinkTalk is invented precisely for the sake of it being a target for natural language translation using a neurosemantic parser. Let me show you how it works. Let's start with just the query side of ThinkTalk. ThinkTalk is a little bit like, in terms of power, it's like SQL, but it is designed differently. The syntax is really designed for natural language translation. So for example, this is how you're gonna say, excuse me, show me restaurants in Palo Alto. You can see that there is a very strong correspondence between ThinkTalk and the natural language. If you want Cuban restaurants, you add a filter, serves cuisine equals to Cuban. And this is how you talk about a top-rated Cuban restaurants. And if you want to only listen to Bob, you say, okay, only if it is reviewed by Bob. What you see here is that a very simple natural language sentence can be translated into a pretty sophisticated query language. And this is important. The representation must be rich in order to to track what we want to say in natural language. And at the same time, we know that these formal languages are complete. Anything that you can answer using the database can be represented in this language, and that is very, very important. And the third thing here is that it is also source independent. So what I have shown you is how we represent a query. ThinkTalk is also capable of representing dialogues and to support end user programming. So for example, you ask for a Cuban restaurant. The sentence that you say in English is translated into ThinkTalk, which is then executed to get the results. The result is read back to the user by the agent in natural language, at which point the user can continue the conversation, such as, oh, please book me a table given the recommendation that was given by the agent, okay? And in this case, we're combining the queries with API calls, and the whole thing is formally represented in dialogues, in ThinkTalk. The whole dialogue is represented formally in ThinkTalk. We also support end-user programming, as we mentioned. It actually supports an event-driven style of executions. For example, when I leave the house, turn off the lights, and this is how you would say it in ThinkTalk. All right, let's see how ThinkTalk is used in a virtual assistant. As we mentioned, ThinkTalk is a formal representation of the dialogue. So, for example, if a user says, I want a cheap restaurant, and it is captured as the input user context representing what has been said up to this point, together with the result. So this information is available to interpret the next sentence. Suppose the user says, I want restaurants that offer Indian food. What I'm saying is that I want something cheap. I want it to be Indian. All right. So this combination, it needs to be generated by the semantic parser. And what we have implemented in our agent is the first contextual semantic parser. It is contextual, meaning that the dialogue up to this current turn is represented formally and provided as context to interpret the next sentence. But if you look at what people are doing with dialogue trees, you're doing intent classification, one turn at a time, it is very brittle. But in this case, because it is a same contextual semantic parser for all the turns, if the user wants to change their mind and start asking questions and talking about other things, it has a chance to also parse that correctly. So that's why that is so important. So the contextual semantic parser turns the natural language into code. Then we can directly execute it to figure out what the answer is. Okay. So in this case, we have some examples of restaurants that fit this description. This information is formally represented and presented to the agent. This is a code that has a policy. We don't want to have an end-to-end neural agent because you want to control what the agent says. So in this case, you code up the agent policy to decide whether you want to recommend a restaurant or you want to ask other questions and so forth. So you decide on what it is. There is a natural language representation and a formal representation. The formal representation goes into the dialogue context, ready to be interpreted as the context for the next input sentence. So this is how we build a virtual assistant using ThinkTalk. So let's summarize the advantages. First of all, it is expressive. It has compositional semantics, and we lean heavily on typed expressions. Okay. So for example, if I learn how to talk about time for reservations, I can use time for appointments. Okay. It is easy to transfer across the domains. It has a canonical and uniform representation, and which is very important for machine learning. And as we mentioned, ThinkTalk is directly executable. It means that it facilitates the agent construction. And it is complete because anything that the agent can do can be captured in a programming language, and that is ThinkTalk in this case. Okay. ThinkTalk is extensible. If what we have right now is not good enough, you can go ahead and extend it because all the tools that we have built are driven by the ThinkTalk grammar. Okay, so now you want to add functionalities to the virtual assistant. It is easy. It's very easy to do. Because our target language, ThinkTalk, is source independent, it is also very supportive of multilinguality. Okay, it is very easy to go and build agents for other languages. And our goal here is to turn ThinkTalk into an open standard language. So this is important if we want to support reuse and support collaboration. I kind of imagine that ThinkTalk is going to be like Java, right? When we first started building web servers, we need a language, and people have created the 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 Java language, and now a lot of the libraries and are available in Java, and that's how we can grow the software industry. And we see that it is absolutely important that we have a common standard so that we can annotate and we can build tools all in the same language so that we can share. All right, so that's the first idea, is that we have to have a formal representation for virtual assistants. The second idea is that we have to be sample efficient. And instead of just relying on annotated data, we rely heavily on synthesized data. We do need annotations of real data, but we need a small percentage. It's about 2% of what people do originally. All right. So let's talk about how do we train a question answering agent. As we said, you give us the domain schema and some representative language, and Genie will automatically just generate you gobs and gobs of questions with the proper annotations because it is all generated. So for making the sentences natural, we turn to pre-trained networks, pre-trained models for NLP. There are a lot of amazing work that has gone on in the last 3 years in developing pre-trained networks. And what they do is that what they are is that they take all the internet sentences and they feed it into these networks, and they use unsupervised learning under various objective functions. And in the last 3 years, we've grown from hundreds of million parameters to, at this point, GPT-3, which is 175 billion parameters. It has read everything. It memorizes all kinds of things from the internet. It knows natural language. Okay, so it is good, for example, in writing new novels, and it can write papers and so forth. But what it doesn't have is really the semantics. It doesn't know what it is actually saying. So for example, if we ask the question, who's the director of Stanford AI Lab? It will come back and say Fei-Fei Li. Well, Fei-Fei was the director of Stanford AI Lab, but now Chris Manning is the director for the last 3 years. Okay, so clearly, you cannot ask GPT-3, for example, to sell you a plane ticket. Okay, we cannot do it end to end. But what it's really good at is that it has statistical language knowledge, and it's just a really good crowdsourced worker. And we can use it to help generate a lot of training data. And so that's what we did. So at this point, we have created a pretty long training data pipeline, pipeline to generate training data. So let me just give you the high level picture of how it works. So you start with the database and schemas. And so, for example, you take restaurants, and it has a field called cuisine. But when I actually talk about the different cuisines, I may not be using the word cuisine. I can express the same thought in many different parts of speech. I may even just say Spanish restaurant. Okay, I never even mention any extra word. It's just a Spanish restaurant. All right, and we now have to map it to that attribute cuisine. So for this purpose, we turn to the pre-trained networks, and we ask it for paraphrases. And we take the paraphrases and identify the parts of speech, and we remember that for every single attribute in the database. Given this information, the next thing we do is that we take all these different parts of speech and put them together in sentences using grammar templates. Excuse me. And we use about 800 templates. Okay, so every language has to have its own templates, but it is domain independent. So these templates will talk about, for example, different kinds of questions, what, when, who, where type of questions, and it knows everything about measurements. We're very big on types. So for example, it understands earlier, later, bigger, smaller, and so forth. So these are generic terminology. So we know all the sentences, and we generate many, many sentences using these grammars by putting all these components together, these primitives together. But the sentences that be put together are very clunky. The next thing we need to do is to throw in the domain specific terminology, and we turn to the pre-trained models to get paraphrases to make them more natural sounding, if you will. So now we have all. This is how we generate a lot of these natural language questions. And we do the same thing with dialogues. We really just keep generating many, many dialogues. We don't have to wait for people to come up with them, humans to come up with them and then annotate them. We just generate these perfectly annotated dialogues and also multilingual dialogues. Okay, so that's the basic idea. I don't have the time to go through all these steps, and let me just talk about the last three parts. So for domain-specific paraphrases, we train a paraphraser by fine-tuning BART. So it takes a synthetic sentence, it generates a paraphrase sentence. But the problem here is that the paraphraser sometimes is not correct, and sometimes it hallucinates. Okay, so here's an example. If I say search for some cafeteria that have greater star than 3 and do not have smoking. Okay, it's a bad sentence, it's clunky. But if you try to paraphrase it, it may generate a sentence like search for a restaurant that has more than 3 stars and doesn't smoke. Okay, now that's terrible. You do not want to train with sentences like that. Suppose I say find restaurants close to my home, it would say find restaurants near me. It is close, but it is not necessarily precise because I may not be home. And a paraphraser can generate you more and more sentences depending on the temperature that you set. But you just cannot choose a threshold because it hallucinates at different temperatures. All right. So at this point, the question is, how do we take advantage of these pre-trained models for paraphrases? We need to absolutely filter these noisy paraphrases. And what we do is that we take the synthetic data that is perfectly annotated, and we train the first semantic parser. We take the synthetic data and send it to the paraphraser, and we get back some noisy paraphrases. But we use the semantic parser to filter out the bad guys. Okay, so it generates some thing talk. We compare it with the original thing talk. If they match, then we admit that as a training sample, and then we train this semantic parser again. And so this is how we do self-training. So you may ask, what is the purpose? You are only using data samples that are known already by the current semantic parser. But the key idea here is that you are confirming to the semantic parser, because everything is probabilistic, that this is a perfectly good sample. Then it will spread its reach, and it will accept more sentences like the ones that you have just confirmed to be a good sample. So that's how we can grow the semantic parser with correct paraphrases. So we ran an experiment using schema.org, and we picked some of the most popular domains, and we train a neurosemantic parser by fine-tuning on BART. So we're taking advantage of all these pre-trained networks. And here is the result. So if you just use the templates, just using grammars, we get to about 50%. These are pretty heavy grammars, okay? But it is still, just 50%. But if you add in the templates plus the auto paraphrasing, we reach an average of about 75%. And then if you compare it with what people can do, if we go to the crowdsource workers for annotations, it is almost the same. So we have more or less reached the same performance of manual annotations. So these are all small amount of annotations. Okay, we are not annotating the full training data. So this is very encouraging. And let's compare this with commercial assistants. We take the restaurant's domain and we ask the same questions of the commercial assistants and ours. And for these long tail questions, it's not just the standard question like, what is a good restaurant near here? Okay. But if we ask a little bit more sophisticated question, which is like, what is the highest rated Chinese restaurant near Stanford? It's not that difficult, but not everybody can get those kinds of sentences. So I've also put in some examples of sentences that we can answer that cannot be answered. So we're pretty happy with the performance of Genie, considering that we just have a small team of a few PhD students working on this. So let's talk about multilinguality. Consider all the work that we have to put in to make the English question answering agent works. What about all the thousands and languages out there in the world? Okay, how do we, do we have to repeat this process for each of these languages? Well, if you look at the commercial assistants today, they have 10 to 20 languages. Okay. But if you look at what we're doing in Translator, the Google Translator has 109 languages. And if you look at the open source Marian MT project, it actually has 500 plus languages. It's an open source system. But I want to caution you in that most of these translators, many of the less popular translators in Marian MT are not very good. The data are not very good. But what it shows you is that there are a lot of people who want to contribute to this effort to make their languages translatable. Okay. So now the question is, can we leverage neural machine translation to create multilingual assistant? Suppose I want to build an Italian assistant. Then an easy thing to do is to use the translation on the fly. You take the Italian utterance, translate it on the fly to an English utterance, then you can go through an English semantic parser and you get to think talk. But what we can do in Genie is that we can take advantage of the fact that the think talk is source language independent. We can take the English training data and we use the neural machine translation to turn it into Italian training data, okay? Because the think talk representation is about the same with the difference of the entities, the parameters. And then we train the Italian semantic parser, and now you can take an Italian utterance, and then you get back to think talk answer. And how does the result? And what does that mean? I want to give you a little bit more details. So you have an English training data, you want to create Italian training data. So in England, you may be looking for a burger, or in America, you may be looking for a burger, but in Italy, you may be looking for a bruschetta. Okay, so what you are looking for and the places need to be localized. They are different entities. And to do this translation, first of all, we send it through the neural machine translator, and it generates a translation, and the entities no longer are the same as the English entities. They don't match the think talk that we have. And so what we do is that we add a liner in the neural semantic part and the neural machine translator, so that we can translate the parameters back to what they were supposed to be in English, matching the think talk. And then after that, we can do a parameter replacement, so we can now have perfectly good Italian sentences and the corresponding think talk sentence. Okay, and that's how we generate the training data. And the result shows that generating, training a semantic parser in the native language is very useful. All right. And with this with this approach, we can create a multilingual question answering agent with local entities in one day. So we hire professional translators to translate about 2% of the English data that we have, because you always want to just not stick with what is automatically translated. The few shot of good annotated data will help it generalize, and that is very important. And so we feel like we now have a handle on how we can create multilingual assistance. And now let's talk about dialogues. Dialogues are complicated because there are so many possible paths. And the standard way for us to do research in dialogue state tracking research is to have Wizard of Oz dialogues. We ask humans to emulate an agent and a user. We take all the English sentences and then we annotate a formal representation for those sentences. And for multi-WOZ, the standard, what was done was that it was just capturing the slot values. It is not the exact semantics. You don't have the actual expressions and so forth. So it is a little bit easier than what we really need in an agent. And what we found is that manual annotation is not just expensive. It actually is error prone. It turns out that with this data set, after 3 rounds of annotations, it still has 30% of errors. Okay, with that level of errors, you just cannot build a very good machine. You cannot train a good agent. So what we do here is that we do sample efficient training. The first thing is that we represent everything that we need using ThinkTalk. Okay. Not just the slots, but everything that it takes to implement the agent in ThinkTalk. It's very large. The space is very large, and we try to cover it using both synthesized data, which is designed to provide coverage and compositionality, and also a small amount of annotated data, which provides the generalization. And how do we generate the data? We use a domain-independent abstract dialogue state machine. So if you look at multi-WOZ, it has many different domains, but they all have the same pattern in their conversation. You start by greeting, and then you say, what do you want? And then you figure out what it is that you want, and then you decide whether you buy or not buy, okay? So this same dialogue state machine can be used in conjunction with the domain-specific information to generate you domain-specific dialogues. And so this is what we do. We just generate lots and lots of dialogues, all perfectly annotated. And this teaches the neural network compositionality. And at this point, we have updated the multi-WOZ to be annotated with ThinkTalk, but we only annotated 2%. We just really cannot afford to annotate the full amount. And with that little bit of annotations, using synthetic data, we reach an overall turn-by-turn exact match accuracy of about 80%. So this is a lot better than what we were able to do with a lot less data. And let's see how this works. The interesting thing here is that the ThinkTalk is very powerful. We found that of the multi-WOZ data set, only 2% of the dialogues is not representable in ThinkTalk. All right. And of course, whatever that is not representable, we do not get any accuracy. We get 0% accuracy for that 2%. And then we found out that about 14% of the turns in multi-WOZ are not synthesizable by our state machine. Okay, the state machine generates things that are very formulaic, but in real life, they always go off script. But with our training strategy with the contextual semantic parser, even though they are not synthesized, we are still getting some degree of accuracy, which is about 60% accuracy on those turns. Now, the rest of the turns are synthesizable, but it doesn't mean that we have synthesized it because there are so many, because the space is so big. So for those that have not been trained, we're getting about 80% accuracy. And for those that match what we have generated in training, we are reaching over 90% accuracy. And this is how we come to 80%. And the good news here is that when you find that things don't work out, you can analyze what is going on, and then you can add more patterns to the synthesis or to the few shot annotation to improve the performance. But this is what you get right off the bat with just about 2% of annotation data. So in summary here is that we have created a toolkit that helps people create these agents very effectively. And our goal here is to empower millions of non-ML developers to create the open voice web. there are 20 plus million website developers. We think that there will be 20 million plus voice developers, and we need to give them the tools. So now let's turn to privacy, okay? So there are a lot of people who are concerned about the privacy implications of the smart speakers that sit in your home listening to everything that you are talking about. But now that with open source, you can just run it locally. And as a matter of fact, I want to tell you that virtual assistants, if we do it right, can be privacy's best friend, okay? Why? So first of all, we have to recognize that if you don't want to share, it's easy to have privacy. You just lock everything up, everything is fine. But Facebook is so big, it's because it helps us share, but it is centralized. Our federated architecture allows you to keep the data and still share. And with the help of virtual assistants, we can share with privacy, with very fine-grained control, and also without disclosure to any third party. All right. Let's talk about what it means to share in real life. Okay. It's not just about pictures. It is everything that we possibly have. People have an interest to share. So here are some 5 examples of things that people may share. And we did a survey with 200 people, and we asked them, would you share this? And a lot, it has a varying degree of people saying yes, all right, for these different purposes. But then we say, what if you can qualify it? Suppose you can say, can your teenage daughter use a credit card if you limit it to $20 budget and for restaurants only? And we discovered that a lot of people would say yes, okay? And every different kind of things that we have has its own set of attributes that you want to control. And this is why you need natural language, because the conditions in which you want to share these things are specific to the attributes, and we need natural language. All right. So these are 5 examples. We've tried many examples, and it shows that if you give them fine-grained access control that is attribute-based, you pretty much can double the amount of sharing that people are willing to do. Because today, people just basically share passwords. Okay. So so we need the access control in natural language. And how do we use a virtual assistant? So to start, we have all the different devices, and our assistant knows how to use them all. So we can issue all kinds of commands, such as monitoring my blood pressure readings and so forth. Okay. Now, anything the virtual assistant can do for us can be shared with with our friends. Okay. So, for example, you want the doctor to look at your blood pressures and your dad to be notified of motion and so forth. And all we have to do is to add in the clause that says, let so-and-so do these things. So they have now the ability to do all these different, perform all these different actions. And at the same time, you can also add extra clauses such as, only if I am not home, right? So this is the access control. So when you give the virtual assistant the access control, then it enforces it. And the virtual assistant is going to do all the commands on behalf of the friend and only share the specific result that you ask, that is allowed with with your friend. And this is how we can just do all kinds of sharing. And the way we do this is that we take the natural language and we translate it into SMT, satisfiability modulo theory, and the conformance is using SMT is verifiably correct. And what we have discovered in a survey of 60 people is that, all the kinds of different things, the qualifications that people can come up with are represented mostly in Think Talk. It's like 85% of what people suggested are in the scope of Think Talk. And this shows that Think Talk is very expressive. So in summary here is that what we have presented is the Open Virtual Assistant Initiative. And what we have laid down is a technical foundation for people to help build this voice, we have the technology to help build the voice web, and also an open assistant to support sharing with privacy. And what we are hoping for is an open voice web, 300 plus languages in 5 years. And I think if we can make this happen, it is going to be better than any proprietary web that can be built. So, well, and I have some contact information here, so please contact me if you have further questions. And thank you for your attention.
Thank you very much, Monica, for this wonderful keynote. Very informative and also very enthusiastic. I like the enthusiasm you put into it. We have just a few minutes left for questions, and here I have several questions. Let me try to select some of them for you. One of them says, auto-paraphrasing not only improves performance, but it also reduces variability across different domains. So in the variability across different domains. So the improvement without auto-paraphrasing was variable across different domains in that bar graph picture you show. However, when you introduce auto-paraphrasing, not only improves performance, but also the variability across different domains diminishes. It's more stable across different domains. Looks like it's an interesting result as well.
Yeah, well, that's a great observation. And you know what is also interesting is that the neural network has a lot of capacity. Mm-hmm. The more it learns, the better it gets. We can just keep learning more and more domains, and it will actually transfer across them as well. So, mm-hmm. So we're very excited with what the neural semantic parser can do, and that was a great observation. We'll look into it more.
Mm-hmm. Another interesting question talks about training parsers with data translated sentences. So how do you manage contextual information when training the parsers with translated sentences? For instance, I remember that I observed one of the examples about food when translated to Spanish mentioning Valencian paella, for instance. However, if you talk about food in USA, you may likely talk about Indian food or some other kind of food. How do you manage this when generating translated sentences in order to train your parsers? How do you manage this contextual information?
Good question. Remember, our tools require people to provide the schema and representative data. Mm-hmm. Okay. So when we do restaurants, we actually scrape the Yelp, we scrape Yelp for many of the languages because there are restaurant information for many different countries for different languages. And mm-hmm. we use that database to supply parameter values in our training. And we actually did something extras for countries that don't have Yelp information. But there's a lot of information online these days, and mm-hmm. We take advantage of it. And the interesting thing here is that we don't really need to have all the values. We just have representative values because the pre-trained networks also know how to generalize across those values as well.
Mm-hmm. Let me find another question from the audience. Taking up big commercial companies with new technology that you open source seems dicey. How do you prevent them from copying you?
How do you prevent people from copying Wikipedia?
Yeah.
I think that if you look at, Wikipedia is absolutely the largest open source knowledge. It's the largest knowledge base. All right. People are contributing because it is open source. Right. Mm-hmm. And I think that, first of all, the technology, these tools, we expect the tools to be used by everybody. We want the companies, the largest companies, to also build upon the tools and to improve the tools. And we keep the tools open source like we keep many tools open source. It's really not, it's kind of well established. But as far as the Thinkpedia is concerned, it is really all about people contributing. And this is open to the commercial assistants too, all right?
Yeah.
And if they find it to be useful, they can adopt it as well. And then lastly is the virtual assistant. I think what would be really nice is to have interoperability, all right? Today, the assistants that we have, they just keep to themselves, okay? But seriously, it is very, very important for the assistants to help us share. And I think we're the first one to put up a protocol. I didn't have the time to go into the details, but we took great pain to make sure that it is secure. You're doing remote execution, but we make sure it is secure so that now we can have very, very fine-grained sharing and across all the different devices that we have. And this is the power of virtual assistants. I hope they will cooperate and interoperate with the open source assistant.
Okay, so there are several additional questions. I'll make sure that I will forward them to you because we have resourced the time. So thank you very much for your wonderful keynote. It has been very illuminating to all of us, and thank you very much.
Okay, thank you so much.